Welcome to Fundamentals of Artificial Intelligence. We are addressing computational issues in making decisions, particularly making complex decisions. In the last lecture, we had looked at sequential decision problems, where the utility is based on a sequence of decisions. Here, solution is not a sequence of actions, but rather a policy, a set of situation action pair for each state. We had focused on accessible environments and looked at a Markov decision problem, the problem of computing an optimal policy in an accessible stochastic environment with a known transition model. We have looked at value iteration, an algorithm for computing the optimal policy, and also looked at policy iteration and alternate formulation to arrive at the policy. In an inaccessible environment, the percepts do not give enough information to determine the state and the transition probabilities. Such a problem is referred to as partially observable Markov decision problem. Exact solution for partially observable Markov decision problems is difficult, and it is possible to arrive at approximate solutions through the technology of decision networks. This is the focus of the lecture today. So, methods used for Markov decision problems are not directly applicable to partially observable Markov decision problems. The standard method for solving a POMDP is to actually construct a new Markov decision problem in which the current probability distribution plays the role of the state variable. The resulting Markov decision problem is not easy to solve. This is because now the state space is characterized by real valued probabilities and therefore is infinite. Exact solution methods for partially observable Markov decision problems require some fairly advanced tools, and therefore we often obtain approximate solutions using a limited look ahead. Now, this can be realized for partially observable Markov decision problems using dynamic decision networks. Before we move on to discuss dynamic decision networks, let us look first on the formulation of a decision theoretic agent. We outline a comprehensive approach to agent design for environments with uncertainty. Now, for such an agent, it needs to tie together belief and decision networks together with the techniques for sequential decision problems that we have looked at in the last lecture. This idea of putting together belief and decision networks address the problem of large state spaces by decomposing the state description into a set of random variables. This is something like the planning algorithm, where logical representations are used to decompose the state space used by the search algorithms. Now, kindly recall that we have looked at the very definition of what we meant by a decision theory in one of our previous lectures, where we have seen that the coming together of utility theory and the probability theory is referred to as the decision theory. The fundamental idea of decision theory is that an agent is rational if and only if it chooses the action that yields the highest expected utility. So, given some actions on which the utility is to be computed, we would love to go via the process of decision theory, where we look at the probability theory and utility theory, and we choose the action that yields the highest expected utility, average over all possible outcomes of the action. The schematic agent design for rational agents is what is given here. We calculate the updated probabilities for the current state, and this is done based on available evidence, which is including the current percept and the previous action. We then compute the probabilities for actions given action descriptions and probabilities of the current state, and then we select action with the highest expected utility given probabilities of outcomes and the utility information. Now, the processing that is done by an agent at each step is called the decision cycle. The decision theoretic agent has to have a number of basic elements, which are the dynamic belief network, the dynamic decision network, a filtering algorithm, and a couple of decisions. The dynamic belief network is about the evolution of the state of the environment over time. A belief network with nodes for each state and sensor variable for each time step. A dynamic decision network brings together decision and utility for actions. We have filtering algorithms which incorporate each new percept and action and update the belief state representation. Now, decisions are made by projecting forward possible action sequences and choosing the best action sequence. The current state of the world under such a scenario is described by the state variables as well as a belief. The state variable is a set of random variables that refer to the current state of the world. For example, if I have an agent which is a robot, let us say moving in the xy plane, then we might use xtyt to refer to the robot's position at time t. And the belief about the state at time t is the probability distribution over the state given all available evidence. So, belief at xt, where xt is the state variable, is the probability of xt given the evidences E1, E2, E3, so on and so forth up to Et. The main assumptions that are required for calculation of the belief are: number one, that the problem is Markovian. The problem being Markovian means that the probability distribution for the current state of the world depends only on the previous state and action in it. So, if I am talking of the probability of xt given x1 up to xt minus 1 and actions a1 to at minus 1, then the Markovian assumption means that the probability of xt would only depend on xt minus 1 and at minus 1, the state and the action just in the previous time point. Each percept depends only on the state at the time. So, percepts are causally determined by the state of the world. So, if I have a percept Et, then the probability of Et would just depend on the state xt. This is the second assumption on way to calculation of beliefs. The third assumption is that the action taken depends only on the percepts and the agent has received to date. So, if I am talking of an action at t minus 1, so all that it will depend on would be the percepts E1, E2, E3, so on and so forth up to Et minus 1. Now, this final assertion is valid because of the structure of the agent itself. Its only input form from the outside is the percept at each time step. Now, taken together, the above equations allow us to simplify the calculation of the current state estimate. The calculation of belief have two phases. One, the prediction phase, in which we predict the probability distribution over states we would have expected given our knowledge of the previous state and how actions affect states, and calculate it by adding up the probabilities of arriving in a given state at time t for each of the state. So, the belief at x t would be the probability of summations of all state time points. So, we add up all the probabilities at time t for each of the states we could have been in at time t minus 1, and here the x t minus 1 ranges over all the state variables during t minus 1. In the estimation phase, once we have a distribution over the current state variables, we are given everything but the most recent observation. So, the estimation phase updates this using the percept at time t. Because both the state variables and the percept refer to the same time, this is just a Bayesian updating. That is, the belief at x t is the probability of E t at x t and the probability distribution of the belief at x t. Now, here alpha is a normalization constant. The decision theoretic agent that we have discussed with its 3 steps now can be looked at in a more detailed way. So, here we would take the percept, we would have a belief network, and we will have a vector of probabilities updated over time. From that, we could create the probability distribution and then the belief itself at x t, and then we would take an action based on the maximum expected utility. The action model, if you see, generalizes the transition model used earlier for sequential decision problems. In the sequential decision problems, we did not use the sensor model. Of course, we did not do that because we assumed an accessible environment in which the percept and the state can be equated. Here, we take help of the sensor model. So, the action model here, it describes the effects of the action, and the sensor model describes how the environment generates the sensor data. Now, sensing in the uncertain world, we are talking of a sensor model, the probability of E t given x t, the state variable. This describes how the environment generates the sensor data. The action model, probability of x t given x t minus 1 and a t minus 1, describes the effects of action, and a stationary sensor model is assumed here. That is, for all t's, we assume that the probability of E t given x t is the probability of E given x, where E and x are random variables ranging over percepts and states, and this could be used at each time step. So, we assume a stationary sensor model in a belief network. So, let us look at a little bit more detail to understand what we mean by a sensor model in a belief network. So, here is a belief network fragment showing the general relationship between the state variable and the sensor variables. So, from the state to the percept, we come via the sensor model. The sensor model actually is the conditional probability distribution table associated with the percept node. If the sensor gives a perfect report of the state, then the sensor model will be purely deterministic. So let's recall the burglar alarm network that we have discussed while we were talking of Bayesian networks. Here John calls and Mary calls can both be seen as sensor nodes for the alarm state variable. Their conditional probability tables shown in the figure here show how reliable these two sensors are. So, in order for a system to handle sensor failure, the sensor model must include the possibility of failure. Now, it is possible to use more detailed models of sensor failure by incorporating additional state variables representing the condition of the sensor.
Anyone with hands-on experience of robotics, computerized process control, or other forms of automatic sensing and control will readily testify to the fact that sensors fail. When a sensor fails, it does not necessarily send a signal announcing its failure. Instead, it simply starts sending garbage. This can be dangerous if taken literally. For example, a robot's sonar distance sensor might start sending infinity, meaning that no object is near its vicinity. This could be because the sonar's detector is broken. In this case, the robot could start crashing into walls. And this is why we need sensor models that allows failure. A sensor model for the sonar sensor that says that the sensor is accurate within some stated distance explicitly disallows the possibility of failure and therefore forces the robot to take the sensor reading literally. For any given actual distance, the sonar model, on the other hand, should allow the possibility that the observed distance could be infinity. Then the robot can handle sensor failure more appropriately. For example, if the robot is in a room and reports infinity, then the most likely conclusion would be that the sensor has failed. Furthermore, if the robot has more than one distance sensor, the sensor fusion process will automatically discount the reading of the failed sensor. The figure here on your screen shows a model of a vision-based lane position sensor. Such sensors are used in autonomous vehicles to keep them in the center of their lane. They also could be used to sound a warning in a human-driven car when it starts to move away from its desired course.
So, the sensor's accuracy in this case that is being shown here is directly affected by an uneven road surface. Furthermore, rain might also cause the sensor to fail by damaging the electronics, as might a bumpy road. So, we are talking of sensor failure which would depend on weather or on terrain, and all of these would somehow impact sensor accuracy. The sensor's failure affects the sensor's accuracy. We know that the sensor accuracy would impact the position sensor, and the lane position would be dependent on the position sensor.
This kind of model is capable of quite subtle reasoning. For example, if the system believes that it's raining, then it will alter the sensor accuracy variable, raising the likelihood of larger error in the lane position sensor. When an unexpected reading occurs, the system will be less likely to assume that the car is out of position. Conversely, a large discrepancy between the expected and the observed position can, on the other hand, increase the system's belief that it is raining without perhaps any other sensor's involvement.
Now, a really serious discrepancy would raise the posterior probability of sensor failure. Hence, this kind of networks can perform some diagnosis of the sensor. Now, let us look at what we mean by dynamic belief networks. First, we shall talk of a Markov chain. Now, an agent can be passively monitoring and predicting a changing environment rather than acting on it. So, the agent is concerned with a sequence of state variable xt values, where each one is determined solely by the previous one. Now, this sequence is called a state evolution model or a Markov chain. Monitoring and prediction is important in its own right, and it also makes the explanation simpler. The agent can use such a model to make decisions and take actions. A dynamic belief network is a belief network with one node for each state and sensor variable for each time step. So, in a real network, the state and the percept nodes would be replaced by several nodes each with appropriate connections, and there would be two tasks for the network. One, it need to calculate the probability distribution for state at time t, and next it would be concerned with how the state will evolve into the future. That is called the probabilistic projection. Now, both these tasks can be carried out using standard algorithms, but a dynamic belief network that we have shown here could be extremely large. So, the belief net algorithms could be extremely inefficient. This is where the idea of using beliefs to estimate and come to the best possible sequence of actions is what is important. So, we have prediction, roll up and estimation, and now we will see the benefit of all the work that went into these equations. We implement the prediction and estimation phase as operations on the belief network. So, this process actually implements the formal algorithms specified in the detailed design for a decision theoretic agent using the belief network inference machinery. So, first you predict, and thereafter you remove some slices at t minus 1 and then formally arrive at the estimation. So, you calculate the belief vector, and this is actually the standard belief network updating process. Thereafter, add a prior probability table for the state variable at time t, and applying standard belief network updating, calculate the belief at xt, the probability distribution over the current state. We then add the slice for t plus 1.
Let us repeat the process of prediction, roll up and estimation one more time. I would particularly emphasize that we implement the prediction and estimation phases as operations on the belief network. Further, we need only structure to represent the two time steps referred to here as the two slices. On the right of your screen, you can see the prediction estimation process in operation. Each cycle of the process go through the steps of prediction, roll up and estimation. We begin with prediction. We have a two slice network. The slices are t minus 1 and t. We have already computed the belief at x t minus 1, incorporating all evidence up to and including the precept et minus 1. The slice t minus 1 has no connection to previous slices. The state variables in t minus 1 have prior probabilities associated with them. We then calculate the belief vector at t. This is actually the standard belief network updating process applied to evidence t minus 1. The next stage is of roll up, where we remove the slice at t minus 1. This requires now adding a prior probability table for the state variables at time t. Now this prior is just what we have calculated in the previous step. Finally, we arrive at estimation, where we add the new percept E of t, applying standard belief network updating to calculate the belief involving xt, the probability distribution over the current state. We then add the slice for t plus 1, and now the network is ready for the next cycle. One needs to realize at this point that this process that we have highlighted here actually implements the formal algorithm that we had specified in the detailed design of the decision theoretic agent using the belief network inference mechanism for all the calculations. Notice that as in the formal algorithm, the percept history is summarized in the belief vector for the current state. Now, probabilistic projection is also straightforward. We take the network and we add slices for the future times. And we then apply a belief network inference algorithm to calculate the posterior probability distribution for the future states given the current percept. Now, one thing to note here is that unlike the update cycle, this might be expensive because here it involves inference in a temporarily extended network. However, a very interesting property of this network that one needs to note is that none of the future nodes has any evidence associated with it. This means that a simple stochastic simulation technique will work well because every run can be consistent with the evidence. Now, as an example of the application of dynamic belief networks, consider again the sensor failure model that we have seen earlier. This can be extended into a dynamic belief network. The figure here shows a two-slice fragment of a dynamic belief network for continuous monitoring of the lane positioning of an automated vehicle.
Focus on the model of the lane position sensor that we had shown while we were talking of sensor failure, and extend the model into a dynamic belief network. In order to extend that into a dynamic belief network, we need to have state evaluation models for static variables, which were the weather, the terrain and the sensor failure, as well as for the principal state variable, which was lane position. Now, the model of interest for us here is sensor failure, and the model is quite simple. We say once a sensor is broken, it usually stays broken. What happens over time is that as the sensor continues to send nonsense signals, it becomes more and more likely that they are incorrect. This is especially true if there are other sensors through which the network can infer lane position indirectly. Now, it will even work, however, just using the state evaluation model for lane position, which will usually put limits on how much lateral motion we can expect for a vehicle. And this is how we could take decisions on what is happening to lane position vis-a-vis our percepts. Now, dynamic decision networks add utility nodes and decision nodes for action into the dynamic belief network. So, the generic structure of a dynamic decision network for a sequential decision problem where the terminal states are 3 steps ahead is shown here. The decision problem involves calculating the values of dt that maximizes the utility over the remaining state sequence, that is at t plus 1, t plus 2 and t plus 3. So, dt minus 1 is treated as evidence because it has already happened, and the final utility would be computed as the sum of the expected rewards that would come out from 1, 2 and 3. Now, here we have not shown the reward nodes just to make the diagram simple. Dynamic decision networks, the evaluation algorithm for dynamic decision networks is essentially the same as that for ordinary decision networks. In the worst case, the dynamic decision network calculates the expected utility of each decision sequence by fixing the decision nodes and applying probabilistic inference to calculate the final state. As in our discussion of sequential decision problems, we must also be careful to take into account the fact that for each future decision, the agent does not currently know what information will be available at the time the future decision is made. In our earlier discussion, we handled this by iteratively computing a policy that associates a decision with each state. With dynamic decision networks, we do not have this option because the states are represented implicitly by the set of state variables, and in inaccessible environments, the agent will not know what state it is in anyway. What we must do instead, therefore, is to consider each possible instantiation of the future sensor variable as well as possible instantiation of the future decision variable. And the expected utility of each decision sequence is therefore the weighted sum of the utilities computed using each possible percept sequence. In a way, the dynamic decision networks provide approximate solutions for partially observable Markov decision problems, where the degree of approximation, as we have seen in our illustration, depends on the amount of look ahead. So, just as we used a limited horizon in game playing and with value iteration and policy iteration, we can limit the extent of forward projection in dynamic decision networks in order to reduce the complexity. In evaluating an action, one must consider not only its effect on the environment, but also its effects on the internal state of the agent via the percepts it generates. So, limited horizon combined with a heuristic estimate for the utility of the remaining steps can provide a reasonable approximation to rational action, and thus dynamic decision networks promise potential solutions to many of the problems that arise in AI systems as we move from static, accessible and above all simple environments to dynamic, inaccessible, complex environments that are closer to the real world. Dynamic decision networks thus provide a general concise representation for large, partially observable Markov decision problems. Overall, the potential payoff of combining dynamic decision network like techniques with planning methods is enormous. The technical and mathematical problems involved in getting it right are difficult, but it is a very important area within AI. In our next module, we should be looking at machine learning. Thank you.